Okay, so good morning, class. So maybe we can just try to start on time. So that would be today's makeup lecture is we're going to talk about another important process, okay, which can govern, like at least you can see eventually is important. So when you look at the aerosol number concentration, so this process called cooculation. So the idea is that cooculation means that you have a two particle, right? So they can hit each other and then stick together, and then they become a bigger particle, right? So this process, so you can see every time when this cooculation occur, right? Of course, your aerosol size will change, but more important, you can affect your aerosol number concentration. Okay, so we're going to talk about this process, okay, in today's lecture. And also, this process is important, especially for those eventually study the environmental chamber study for aerosol formation, right? In the environmental chamber, so basically you can inject some aerosol into a chamber, and also maybe you can form the SOA formation, right? But the important is that you have these, say for example, these particle around, and then they can just have this kind of a cooculation can happen. So this can largely govern your aerosol or particle number concentration. So this is in particular important for those who study the environmental chamber for aerosols science, okay? But let's talk about this process for today. So we're going to talk about is called the cooculation. So like I mentioned, right, cooculation means that you have a two particle. So you have two particles, right? And then they can come to each other, right? For example, you can assume, so one is a stationary, and then the other ones, you can just move towards to this stationary particle, okay? Stationary means that they just you just assume this particle is fixed, right, at this position, and then you assume just a simple discussion. So you can just argue. So you have a particle at fixed position, and then you have another particle and can diffuse to the particle, and you have this kind of a collision, right? And then if you look at these, cooculation can happen, right? So you can argue. So that means that when they touch each other, right? So this is called the cooculation can happen, right? So you can also argue. So let's say we assume two particles. Sorry, not very spherical, but try to draw like. So you have two spherical particles, right? So they can just come to each other. Okay, and then once they touch each other, right? So they can have this kind of a stick together. So first, we're going to talk about this kind of a cooculation. One thing is, of course, so there are different types of cooculation. So one thing today that we're going to talk about is called the Brownian, kind of the Brownian diffusion cooculation. Okay. So like I mentioned, this is particularly important, say when you have a chamber, so you don't have kind of a convection. So the particles are mainly, the movement is due to the Brownian motion, right? So therefore, we're going to talk about today is that kind of called the Brownian cooculation. Or you can say the particle is moving around by some Brownian motion. Okay. So basically, what we try to do now is for this cooculation. So one thing we are interested is to look at, right, the rate, right, the rate for this kind of a collision, right? So we want to look at the rate, right? So at which the particle, right? Say collided with this, we say a stationary particle. So we start with this, okay, and then we can relax this assumption. Say, for example, so we assume you only have one stationary particle, and then you have a number of particles at the same side, so they can collide with this stationary particle, right? So we first look at this collision, and also looking at the collision rate here. Okay. So now you can see, so now we're looking at this collision rate. So this happened, right? So you can argue when they touch each other. And also you can just draw another way. So I think this is the way they also present in the lecture notes or in the textbook. So you can argue, right? If you look at just the graph here, so when the two particles have the same sign, right? So they collide with each other. So this can also be considered like you can argue, right? So these are figures, okay, you see from here. You can also argue, right? You can have a particle with the radius, right, of 2rp, right? So because we assume all the particles have the same size, okay. And then when this collision happens, you can argue, right? So you can have a particle collision, and then we have a point particle just hitting the surface, right? So you can also see that this is a. You can also argue mathematically, so you can have a point particle, right? Just a point, it just hit the surface, right, of a sphere. So with the 2rp, right? So just because we assume all the particles same size. Okay. But first, we want to look at these limited cases or simplified cases. But of course, later we're going to make it more complicated, right, or to be more realistic situation. But now we just start with this. So you have the particle of the same shape, and then you have a stationary particle, and then you're looking at the collision rate of a particle, right, of the same size, hitting this particle, right? So we're going to do this analysis. Okay. So first, to look at this is we also consider, say, in this continuum regime. So we know that depends on the particle size, of course, the mean free path. So we can have a continuum regime, kinetic regime, or transition regime. So we start with the continuum regime. And also we need to assume, okay, or to understand, say there's a distribution, a concentration of the particle. So around this stationary particle, right? So we need to know the concentration or distribution, okay? So let's say we make some assumption, okay? And then we assume the distribution of the particle, say around this stationary particle can be described by some continuum diffusion equation. Okay, so let's say we assume distribution of the particle, right? Say around this stationary particle. So we need to know the concentration profile, right? So around this particle. So let's say you can be described by a diffusion equation. Okay, we call the continuum because of the continuum regime. So we can describe by some continuum diffusion equation. Okay. So then you can looking at this. So this is the concentration of the particle, right? Say around the stationary particle. Say the R is the radius, right? So let's say R is the radius at different time, right? So you can have so if you choose the R as a coordinate, so this is the continuum diffusion equation. So this is describe the concentration, right, of the particle, say around this stationary particle as a function of time. So it can be related to this And the only thing is, I think we know this, right? So this, the D is the diffusion coefficient, right, of the particle. So because it is a particle, right? So you need to have a diffusion coefficient, right? So to describe this, a Brownian diffusion. So therefore, this the D is the Brownian diffusion coefficient, right, for the particle. Okay. And then this is the equation. Okay. Then of course we want to solve this diffusion equation. So we need to, this is the partial differential equation. So you need to have some initial condition, right? So we can set some initial condition. Right, so we need to have some initial condition to solve this diffusion equation. So the first thing is you can have n R0 equal to n naught. So n naught is your initial concentration, and then you assume the concentration, say, along this R coordinate, right, along the radius at time equal to 0. That means at the beginning, right, will be equal to this is n0. Okay, so that means the idea is that you have this kind of what we call homogeneous distribution. So basically, that means that you have the uniform, right, concentration of your particle along the R, right, coordinate, okay, or direction at the beginning, right? This is time equal to 0, means at the beginning. And also, you can also argue for any time, okay? So if the particle, say, is distance far away from the particle, right, infinity, at any given time, so there will be no change. Okay, so equal to n naught, so they're same as your initial concentration. And also there's another condition, so we can set so you can see that the concentration of your particle, say at R equal to 2 Rp, right? So now we kind of using mathematical to calculate this collision. So let's say you have a particle, right, in this case. So when you have this 2 Rp, right? So that means that you have this kind of a collision happen, okay? And then you remove the particle, okay? So therefore you set these. So at any time, so when you have this collision happen, right? So it will be set equal to 0 here, okay? So basically here means we can also argue these we call the stationary, or we say the fixed particle. Okay, so it's a perfect absorber. Okay, so that means that every time you have this collision happen, like they just stick together. Perfect absorber. So basically means because of course in reality, so I think intuitively you can think about, so when you have these two particles, they hit each other, right, or collide with each other. So of course some of them will bouncing off, right? So they will separate again. So but these we just assume every time with the collision happen, they just stick together. Okay. And this may be also a good assumption. Because now we are not looking at some strong convection, right, transport phenomenon. So we are looking at some we call the Brownian cooperation. So usually this particle, okay, if you look at just some Brownian motion of the particle, so usually they are not very, let's say, have a lower kinetic energy. So therefore, this is still a good assumption, okay, in some sense, to some extent. Okay, so now you have this continuum diffusion equation together with this initial condition, right? Then you can solve the distribution, right, of the particle, say around the stationary particle, right, at different position. So then you can using this equation together with this initial equation, and then if you solve this, so I just present you the solution. So the solution will give you the concentration of the particle at a given radius, right? At a different time. So this is the solution for the continuum diffusion equation together with the initial condition that we discussed. So it tells you the concentration of the particle, right? Around the stationary particle as a function of time, also the distance. So we get equal to the n naught, your initial number concentration, right? And then equal to 1 minus 2 Rp. Remember, the Rp is the radius of your particle, and then divided by the R. So this is the ERF is the complementary. Just to remind you, so I think we know, so you have the C here, so this is the complementary error function. And then with this input like R minus 2 Rp divided by 2, and then you take the square root of this called the diffusion coefficient, right, of the particle times the T. Okay. So complementary error function just a 1 minus the error function, right? So you know this term here. Okay. So now you have the equation, right, to describe, say, the distribution of the particle around the stationary of particle, of the fixed particle, right? So of course, now we are interested in the coordination, right? So we want to look at the rates of the collision, right? Because this kind of a rate of collision can give us some idea, right, about the cooperation. Okay. And also we are looking at this rate of collision is you have a fixed particle, right, and then you have a number of particles around, and so they will collide with this we call the stationary particle. So if you look at the rate of the collision. Okay, so say this is a J equal to the rate of the collision. So if we want to calculate, right, the rate of the collision, of course, the rate of the collision is you can see some of the terms in this equation is of course you are looking at some of we call the effective surface area, right, of the particle, because this is the area, right, for your collision to happen. So therefore, this is the kind of we can say this is the targeted, right, surface area for collision. So therefore, you can have a term. So you can say the first term here is a kind of the effective surface area of your fixed particle, right? That means your stationary particle. And now, of course, this E is the diffusion coefficient, right, of the particle. And then you're looking at the rate, right, of the concentration, the gradient, right? And then, of course, I'm looking at the surface, so that would be set equal to R equal to 2 Rp. So now, because you have the equation, right, for the distribution of the particle, so you can take the derivative of this one and then set R equal to 2 Rp, and then you can substitute back to this equation, and you can calculate, right, the rate of the collision, right, so in this case. So if you solve this, you take the derivative, okay, with respect to R, and then you set R equal to 2 Rp here, and then you substitute to this. Okay, so now if you're solving this equation, so this is the equation, okay, for the rate of the collision of the particle, right, to a fixed particle here. So this is the rate of the collision. Okay. So now you can see the rate of the collision, okay. So that would be equal to 8 pi times this RP. So of course you can have some idea about the RP here. It's a kind of related to the surface areas, and then the diffusion coefficient, of course, are related to the concentration of the particle using the anode, and then it's equal to 1 plus the 2 RP over the pi, the square root of the pi. D means the diffusion coefficient of the particle times the T, right? Because the collision rate will also change with the time. So if you setting these, one thing, if you look at this equation, right? This rate of this equation, I think you can get some idea, right? Quickly, you can find something. So I find that you will see that if you're looking at this rate equation, so let's say at the beginning, right? At the very beginning. So when your time is very small, okay, at the very beginning. So say your time is very small, or say the time tends to 0. So that means at the very beginning, right? So you allow the collision can happen if you have certain conditions that we described. So if your time is very small, or at the very beginning, so very small tends to infinity, tends to 0, right? So if this term tends to 0, so what will happen? So this term becomes very small, right? So you take the divided by a very small term. So the whole term here is big, right? It's very large, okay? So therefore you can argue, right? So if at the very beginning, right, you can see that sometimes if you put it close to 0. So the collision rate, the idea is the collision rate is very fast, okay? At least you can see that it's a very fast, right? So of course mathematically, so it can be very big number, okay? But the thing is that you can see when times go on, okay, or say when the T increase, right? So when the time proceed, okay. So let's say you can also pick some condition. So let's say if your times, you get this term. So when your time say larger than 4 pi r squared over pi d. So why we set this? So when the time say much larger than 4 rp squared and divided by pi d, if you substitute these terms here, okay, so you will find that now these terms, right, will become insignificant, okay. And then you can say that now you can kind of approach we call the steady state, right? Because you can do this substitution here. So when this t becomes much larger than this term, because you take the square root, right? So this has become a big term, and then you divide it. So this term becomes insignificant, okay? Or you can just argue the time increase, okay? And the time increase, right? So no matter what, so under this condition or not, right? So when the time increase, right? So this term will become insignificant, right? So you can also argue, right? So we can say that we can kind of reach a steady state. And then your collision rate will just equal to this term, right? Okay, so does it make sense? So that means that given some times, okay, so then the collision will kind of reach a steady state. Okay. Are you okay with this? But of course, I just want to remind you that so when we derive this equation, right? Of course, we assume the one particle is stationary, right? So we only consider the collision. So you have fixed particle, so then you have the particle of the same sign around, and then you have this kind of a collision, right? So we are looking at this the rate of collision. Okay, so of course we can kind of relax this assumption later. For example, so these two particles, right? So you can have a different size, right? And also we are not just looking at one particle, right? So of course you can have a number of particles. So we want to look at is not just the collision, right? For one stationary particle. So we want to look at the total collision, right? Because you have a particle distribution, right, of a population. Okay, so we're going to talk about this. So remember, just like I mentioned, right? So this kind of this equation I show you here, it's just to look at the rate of collision, right? For a single fixed stationary particle. Okay. So now you also want to be interested to look at the total collision, right? So we want to look at the total collision. Okay. So of course here we're also looking at all the particles have the same size. And now we want to look at all the particles, right? So because now we're just looking at one particle, we want to look at all particles. So one way to doing this is because you can say here is implicitly, this is just at one particle here, right? So then if you want to look at the all particle, right? So you just times the total number of particles you will have. So therefore, if you want to look at the total collision, say C here, so you just say time the number concentration of the particle, right? Maybe most of the time, so usually we write like this. N times n, right? Because the initial equation just describes just one particle, so we just have you can times the total number of particles, right? That's another n, so therefore that will become squared here. So now you are looking at the total collision, right, of the particles. Say you have n number of particles. Okay, so this equation will give you the total collision, and then of course we still assume all the particles have the same sign. Okay, so this gives a good calculation for your total collision. Okay, so now you have this kind of a collision rate, and also like at the very beginning, right? So one thing we are interested to look at this kind of a co-population is so every time when this collision, right, or co-population happens, so it will reduce the number of particles, right? So for example, initially we have two particles, right? So initially we have two particles, right? So of course after the collision, so we will have one bigger particle, right? So, but in this case, of course, your size will change. But the one thing is that you also decrease your number, right? So you also decrease your number concentration, right? So you can every time you have this happen. So that the argument here is you can see every time. So when you have this collision happen, so your number concentration, right, will decrease, right? So therefore, we also want to look at, say, so what will be the total number concentration change, okay? So we also want to look at, see how the number concentration changed due to the collision. One thing you can also argue, you can also see that every time when this collision happens, right, your number decreases at the same rate, right? One thing you can find that number of your particles will decrease with the same rate. Okay. because you can always argue that every time, so when this collision happens, right, your number will decrease by 1, right? Will decrease by 1. Because every time you have this collision, so your particle number will decrease by 1, right? So therefore, you want to look at the total number concentration, right? So now you're looking at the total number of concentration of the system change with time. So then that would be just equal to your collision rate, right? The total collision rate. So here, usually people will group some of these terms. And then they will just write in this case. And then they just apply this term they call the cooculation coefficient. Okay. They call this a cooculation coefficient K0. And then the K0, you can see from this, right? So they will just set equal to 8 pi RP. RP is the radius of the particle, P is the diffusion coefficient of the particle, right? So they just set a term like this. They call this a cooculation coefficient K0. Okay. So now we want to do some analysis to look at this term here. So we want to just look at this term. Because if you look at this cooculation coefficient K0, so would be equal to 8 pi RP. RP is the radius of your particle, and then D is the diffusion coefficient, right, of your particle. We want to say, look at this, right? This will give you the cooculation coefficient, right? So now we want to look at this term, the diffusion coefficient. Okay. So if you look at this diffusion coefficient, so we can also, if you remember, right, so we can find a way to calculate this diffusion coefficient, right, for your particle. Okay. So one way to calculate this diffusion coefficient for the particle will be equal to K times T times B here. So K, if you remember, the K, small k here, it's not the rate constant. The K here is the Boltzmann's constant, right? So the small k here is the Boltzmann's constant. And then the T here is the temperature. And then the B here is the mobility or the particle mobility. So it's the particle mobility. So if you remember, right, so for the particle mobility, the idea is that you try to apply a force, right, to a particle. And then if the force times this mobility, right, so give you the velocity, right? So this is a kind of a physical definition. So if you remember these terms, I'll just remind you, so for the particle mobility, right? So this is the B here, so we just discussed. It's just equal to V over FB, right? So F is the velocity, so V is the velocity, F is the kind of the force, right? The drag force. The D means the drag force, right? F on the particle. So if you remember, if you have not calculated the drag force times the mobility will give you the velocity here. Okay. can calculate these. So you can see here is the B, if you remember, so that may expand this term, so that would be equal to this Cunningham correction factor, right? So the size divided by 3 pi, this mu here is the viscosity of your fluid. And then now, if you remember, we use the dp is the diameter of your particle, right? So this is how we can calculate the mobility, okay? So now if you substitute these information back to these terms, right? And then you can just also put this into this term here. Okay, so then you can calculate, right, your population coefficient. So we just what I did here is just to do the substitution. Okay, so we just substitute all these. And you can calculate these population coefficient will be equal to 4 times the K. Remember, the K is not the rate constant. K is the Boltzmann's constant times the temperature times this we call the Cunningham correction factors divided by 3, and then this is the viscosity of your fluid, right, or the air. Okay. But of course, I just want to highlight here is when we derive these terms, so I just want to remind you is we still assume, right, all the particles have the same size, right? So this is what we just assume, and also we are in this we call the continuum regime. Okay, so this is how you get this here. But of course, you can also argue, right? So, so when the particle getting smaller and smaller, so we are not in the continuum regime anymore, right? So sometimes, so we can go to the kinetic regime, or we call the free molecular regime, right? So therefore, this kind of the cooperation coefficient, you need to do the correction, right? So one way to do this is people just you have this K, and then times a beta, okay? So beta just some correction. So remember, you derive this correlation coefficient, say in the continuum regime, K naught, and then you just times the beta, and then you try to look at this correlation coefficient in the free molecular regime. Okay, so this is the free molecular regime. Okay. So of course, these beta, okay. You can say this is a correction factor. So different studies and different groups on the literature, you have different expressions. But one thing people just you can have a different expression. I'll just show you one here. Okay, this is just one of the way you can do this correction. This data, so you can find this. You can using this expression, just one way to do this correction. But now this is KND, so this we know the Kn is called the Newton number, right? So you know the definition. But here they just find another way called the Newton number KND. Okay, the KND just you do the calculation by using these terms. So this is the 4 times the diffusion coefficient of the particle, and then you divide it by the square root of the 2. So this is your thermal velocity of the particle, and then this is the size of the particle. So that's why the size correction is in this term here, dp here. and then you use calcium this that we call the KND, and then you substitute to this, and then you calculate the beta, and then you do the correction. Okay. Does it make sense? Okay, so but the general idea is if you want to look at the correction term, so how this, say the K value, right, in the continuum regime and also the free molecular regime, right, so how they will change, or how this beta will change with the size, right? So of course, so when your particle size is big enough, okay, so then you are in this continuum regime, so your beta will be just a 1, right? So your size of large particle. It turns out that so when your particles getting smaller and smaller, okay, this kind of a cooperation coefficient will decrease, okay, in this free molecular regime. So later we're going to talk about this when your size getting smaller and smaller, okay, and also what factor will affect this kind of a collision coefficient. But one thing is that you can see so how this correction factor change with the particle size. So dp is the particle size. So this is a micron. So this is say from very small particles, they put us upon 0.01 to 10 microns, so large particle, right? So of course you can argue. I have to put it on. Sorry, this one here. So you will find this kind of correction. So of course, I think we know, right? So because we derive this phenomena in continuum regime, like I mentioned, so for large particles, so the beta should be close to 1, right? So because it's just in the continuum regime, so that would be just K will be equal to the K naught, so the beta will be equal to 1 for large particle. For small particle, it turns out this coagulation coefficient will decrease when the size is getting smaller and smaller. That means they are more difficult for this coagulation to happen for a small particle if they have the same size. Okay. So any questions for that? So, but the only thing I is that it's more important for you to get kind of an idea is when the size of particle of the size getting smaller and smaller, it turns out that if they have the same size, they become more difficult for the coagulation to occur. Okay, so you can see from this graph. But of course, you can have a different expression here. So this is just one way I show you. Okay, and also just want to go back to this term. So like I mentioned, right? So when this coagulation can happen, so your number of particles, right, will decrease over time, right? So you can see because like a statement which stay here, right? So every time, so if we have this kind of a collision can happen, right? Your particle number will always decrease by 1. So therefore, your number concentration, right, your total number concentration, change with time, okay, will be just equal to minus K naught. So now the idea, right, this is called the coagulation coefficient. And then you know how to calculate or what's the ideas of this K naught, and then times this N to the power of 2, where N is the number concentration of the particle. So maybe we can just also solve this equation. Solve this equation. So this will help us to understand, say, how the concentration changes with time, right? Okay. So now, so let's say if we're interested to look at the temporal profile of the particle number concentration. So that means how your number concentration of your particle changes with time, right? So I can just rearrange this equation. Okay, so I just rearrange this equation. I put the delta t on the right hand side, and then this n square I can go to the left hand side. I can then set the initial condition, right? So the time from time 0 at the beginning to certain time t, and then I have my initial concentration n naught, and then my concentration at time t, right? So I just can do the integration, right? So I think this is a kind of a straightforward, and then you can solve this equation, right? With this two initial time equal to n naught and different time t equal to np here. So if you solve this equation, so this will give you how your concentration, right, the number concentration change with time. So by solving these, so the concentration of your particle at a given time t will be equal to n naught, is your initial number concentration, divided by 1 plus the n of your initial number concentration times your cooperation coefficient. And then, of course, it depends on the time t here. Okay. But of course, one thing, of course, we know from this equation, or we all understand is when your time increase, right? So your number concentration will decrease. Okay. So then, if you plot this graph, so let's say I try to plot at different time. So time, this is time. Of course, remember, usually time you're not in the log scale, so usually it's a linear scale, right? So, but this is the time. So this is a 1 second, 1 minute, 1 hour, 1 day, or you can set 1 week. Okay. And then you look at your n, that means your number concentration. Okay. So if you're looking at these equations, so of course, in the first few seconds, so you don't have much change, but when you have time increase, so you will have a number concentration like this. And also you can see from one term, you can also see from here, right? Some analysis you can quickly identify is if your T is large enough, long enough, right, in a system, in closed system. So what will happen is if the time T is keep increasing, eventually, right? So you just have one large particle, okay, because it's all the particles just stick together, right? So you can have this kind of a curve like this here, so over the time. So any questions so far? Okay. Also, like I mentioned, so of course we are interested to look at how the number concentration, right, decrease over the time due to the coagulation, right, of the particle, right? So you can show it here. So of course you can try different n naughts and then you just plot the same graph, but eventually given all the different long time enough, right? So they will just overlap, right? Because eventually, so they will just give you a few particles, right, due to the coagulation. If your time is long enough, okay. But one thing is that we also are interested is we just like I mentioned, right? So of course you will reduce your number, right? You will reduce your number, but you also will kind of change your size, right? So your size will also change, right? So because you just stick together, if you merge, right? For example, you can imagine you have 2 water droplets. So they hit each other, right? So they will merge and then become a larger liquid droplet, water droplet, right? So you have a larger size. So we want to look at how the size change, right? And how you can relate it to the number change. To do this analysis, we want to make some assumption here, okay? So let's say first we assume say for your system, okay, your total mass of your particle remain constant over time. So let's say the total particle mass is a constant over time. So you don't have any loss process here. Okay. So that means if your mass is the same, so let's say this concentration of your mass is the same. So let me write down the equation and I will discuss with you. Okay, so I just will do a very simple rough analysis. Okay, so in this case, what I want to do now is, so we know when you have these two particles stick together, so the number increase and then your size will increase. So I want to look at how your number concentration change, and then how you affect the size change of your particle. Okay, and then here I assume in our system, okay, your total particle mass are the same. Okay, over the time. So therefore, this is N naught is the initial, right? Initial number of the particle, and then you assume all the particles have the same size. Okay, so therefore, and then you have the BP naught. So you can argue this is your initial particle size. All the particles have the same size, all right? So this will give you the volume, right? And then you times the rho P here. Rho P is the density of your particle. So this will give you your initial, right? Your particle mass, total particle mass here. So this term tells you the number, right, concentration at a given time t. And here I assume all the particles also have the same size, right, at this given time t. Okay. So and then if you just also do the same thing, so this is the number concentration at given time, and then this is the size of the particle at a given time. So all particles are the same size. And then you have the density, right? So if you time these two terms, they will have the same mass, right? So because I assume the mass is constant. Okay. So basically, you can just try to rearrange these two equations, and then you can find out that some terms so we can cancel, right? So you don't need to worry about the pi over 6 and also the density of the particle. So if I try to just look at the ratio, say I want to look at the ratio of the particle at given time t to the initial particle size, then you will see that it will be equal to, and then just also your initial particle number concentration divided by the number concentration of your particle, right? And then you take the 1 over to the power 1 over 3, right? So this is how we related here. But how to interpret this result? So you can argue, right? So in case, so if we want to say double our size, okay. So in this case, so let's say I want to double my diameter, double my size in the diameter. So this is become 2, right? Because I want to increase to 2 dp initial or d naught here. So in the size. If this is the 2, and then you can see that somehow your particle number concentration has to be reduced. So if you look at this, if you set this is equal to 2, okay, and then you have this 1 over 3, right? So you can do the calculation. So you will find that if I want to doubling the size, say the diameter, say now this is become 2 dp naught, okay. So the reduction, so this is the reduction. If the particle number would be by a factor of 9. Okay. So you'll see that your number concentration has to be reduced by a factor of 9. And then in that case, if we take this assumption, you can see your size will increase, say double here. Okay. So that means, but remember this analysis, we assume all the particles at the same size. So therefore, you can see that, so to double the size, so that means, so that the idea is that you can to increase the size. So you can see that you need to have a further reduction, okay, in your particle number concentration. So in case that we want to increase the size. Does it make sense? So any questions so far? So I think so there's some idea is for you to have at least get this moment is of course we do the analysis. So say assume all the particles have the same size, right? But we're going to relax this after the break. But at least now you have some idea about the cooperation coefficient. And also I think the most important message is that now you have the idea is so when you have this cooperation happen, right? So your number concentration will decrease. Okay, and then it can take a long time. So eventually, just maybe only have one big particle, right, so in your system. And also, of course, when you have this kind of a collision happen, your size will increase, right? Because like I mentioned, an example is that you have two water droplets, right? So when they hit each other, they merge and then become a larger water droplet. So these are simple analysis just to give you some idea. It's, if you really want to increase the size, it turns out that so we need to have some larger extent, right, in your particle number concentration reduction. Okay, so this is the message. Okay. So after the break, so we're going to talk about, because here we still assume two particles have the same size, but of course in reality, so you have a different size. And also you will see that if they are different size, so that can have a huge implication for your cooperation coefficient. Okay, so that will be depends on, say, the ratio of the diameter of these two particles. So you will see this. So we're going to talk about this. This is another important message for the cooperation. Okay, because remember, cooperation will involve the collision of two particles, right? So they can have different properties. In this case, they can have different size. So then you will find that if the size will have an implication for this cooperation coefficient. So we're going to talk about this after the break, okay? So, but before we take the break, so any question from the class? Okay, if not, we're going to take a 10 minutes break here, and then we'll come back at 12:37. Okay, so we'll take 10 minutes break. So after the break, so we're going to talk about the cooperation with two different sides. The cooperation, right, of two particles always at the same size. But of course, this is all in reality, right? So you can always have a particle with different size. So in this case, for example, you can argue. So this is your LP1, and then you have an LP2, right? So you can have a different particle size. Okay. So now we want to look at, say, the cooperation, okay, with different size. But of course, so we're going to go through very quickly. So basically, we can apply the same equation, right, or same approach. So we apply for the particle with the same size. But now, of course, we are looking at the diffusion equation again. But of course, now we are looking at different particle size, right? Particle size. And also, in this case, we can say, we assume you also can argue, right? So you have a diffusion of your N2. So that means that, let's say this is N2, so this is N1. So you can have some diffusion of the particle, right? Type 2 or N2 to a stationary, right? Or respect to, or relative to N1 in this case. Okay. So therefore, you can still writing these using some diffusion equation. So again, this equation, diffusion equation, we just to describe. So let's say you have a diffusion of your N2, say let's say relative to your N1 particle here. So the diffusion equation would be just say looking at the concentration of your N2, right? Say around your N1, so just like we discussed before, at different radius and also say at different time. So I'm sure you will know, basically you will have the same equation, right? In this case, but the only difference is this diffusion coefficient, right? So because of this diffusion coefficient, so you are talking about the diffusion of your N2, say, relative to the N1, right? It's different here. Okay. So then this equation, if you try to solve this, that will give you the concentration, right? Say of your N2, say around your N1 particle at a different time and also at a different radius, right? Say away from the center of the N1 here. So of course, you also get the same initial condition. So I think we just go through quickly. So because you can see the only difference in the equation is just this diffusion coefficient, right? Not just the D. So now this is the diffusion coefficient. 1, 2 means the diffusion of your N2, say relative to N1 here. So also you can set the same initial condition before, like the N2, right? At a given distance, at any given distance at the beginning, right? We just equal to N2 naught, right? So we have this kind of a homogeneous distribution. And also if the N2 is say infinity at a different time. So that means that if your N2 say far away from your N1 at any time, we also the same constant, right? Also called N2 naught. And also we're looking at the surface, right? So now remember, so we are not just a 2RP1, right? Because you have two particles with different size. So therefore your N2. So now you are not looking at just a 2. It's RP1 plus RP2, right? So because they hit each other, right? So you draw the particle. So that would be RP1 plus RP2, right? So this is how they contact with each other at any time. So that means every time. So when you have this collision happen, right? So we just assume you have a perfect absorber here. So if you consider all these information, right? So you can solve in these, and then you just give the equation. Let me write down here. So you will still have the very similar equation, right? We have for the particle with the same sign. So this equation tells you the distribution, right, of the N2, say around with this N1, right, will be equal to N2 naught, and then you times this function again. So now different is you just use the sum of the radius of these two particles, right, with different size, divided by the R. So this is a complementary error function. And then now this is again the sum of the diameter of, in this case, the radius of the two particles, right? RP1 and RP2. And then diffusion coefficient, remember, so you are looking at the diffusion, right, of your N2, say relative to your N1, and then we have this times T here. So this equation just give you again, so the distribution of the N2, say around the N1 here at a different time. Then we can just solve this equation. So again, we are interested to look at is the rate of the collision, right? So therefore, so again, you can just calculate the rate of collision. So basically, you get the same results, but the only difference is some parameter changing, right? Because we are looking at different size. So this is just the collision rate, right? Say we assume just at the steady state, okay. So that will be equal to, now if you remember, so these terms is more give you the idea about the effective surface area, right, kind of for the collision. So now it will become sum of the radius of your R1, RP1, and your RP2, right? Because you have a particle with different size. And then this is the diffusion coefficient, right? Of the N2, say, relative to N1. And then this is your N2 initial concentration, okay, then you just times this 1 plus. So again, remember, so this will become RP1 plus the RP2, and then you have this divided by the square root of the pi diffusion coefficient again times the T, right? So because the collision rate will change with time, okay? So this is the case. But remember, so when we derive this, is we just assume the number of collision, right, of the N2, say with one fixed, right, or one N1 here, right, just one particle. Again, so if you really want to look at the total collision rate, right, so just nothing fancy here, total collision, say between N1 and N2, right? So let's say you want to look at the total collision, right? These two type of particle. So we just times another N1 naught, right? So this is the case. So here is again, so if you want to study the steady state, here means because you meant, so I think I mentioned wrongly before. So basically, this is the general equation, right? So this is the general equation. We just solve from this, right? And by looking at the collision rate at the surface, right? So we skip some of the steps. I think it's just basically just follow the approach. So right, we derive for the particle with the same size, or I assume. So you know how to get this collision coefficient, right? But this is a general equation. So sorry for that. Is for steady state, that means your time go to it process a certain time. So you don't need to worry about this. So then your collision rate is equal to this term, right? 4 pi times the RP1 plus RP2, right? The effective area for the collision. And then you have this D12, so the diffusion of the N2 relative to N1, and then you times this N2 naught, right, for initial concentration of the N2. And then if you want to look at these, so that's why I want to remove this steady state. So because for the steady states, so you basically, if you remember, we have the discussion, right? So this term, so when your times increase, right, so this term become insignificant. So we can reach a steady state. So this will be this term. So then if you have this, I want to calculate the total collision, right, between the N1 and N2, right? So basically, because of this equation, just for the collision, right, of the N2 to one stationary N1 here, just a one particle, right? So therefore, you want to look at the total collision between N1 and N2, you just have times your N1 naught here, right? So that will give you the total collision here. And also you can see that now I want to change the rotation here is I use the J12. So that means now we are looking at the collision between N1 and N2, right? These two types of particles with different size. And then you can see here is now you can put these terms together, right? Just like what we did for the particle with the same size. So we can put these all terms together. And then you can get a term called K12, right? So this is, we are talking about the collision between two particles, right? Different size, 1 and 2. So therefore, you can just, people usually rewrite the equation would be just, so when you're looking at this kind of collision, right? Or cooculation, J12 will be equal to some, we call the co-occlusion coefficient, right? For these two particles with different size, K1, 2, and then times their concentration, right? Or the initial concentration in this case. Okay. But now, again, so we want to do some analysis for your K1, 2, right? For this term, right? For this term. So one thing like we did, right? For the particle of the same size is that this diffusion coefficient, right? This is a Brownian diffusion coefficient. So one thing is if you want to determine this, we call this diffusion coefficient, right, of N2, say, relative to N1, okay? So some things people will try to expand these is okay. So let me explain this term here. Okay, so of course now people you can use the radius most of the time. So in this case, I just changed to the diameter. So therefore, you just you see the pi change here. So nothing changed here. You just change from radius, okay, to the diameter of the particle 1, and this has become the diameter of the particle 2. So now this is your D12, right? So this is the, again, from time to time I mentioned, is the diffusion of your N2, say, relative to N1. So this is called the D12. So actually D12, you can calculate the D12 just equal to D1 plus D2. Okay, so this is how you can calculate the D12 here. Okay, if you want to calculate this D12, that means the diffusion of the N2 relative to N1. So you can calculate the diffusion coefficient of the N1 plus the diffusion coefficient of your N2 here. Okay. And then one way to calculate this diffusion coefficient, so let's say because we are talking about the Brownian, right? Brownian diffusion. So we just show another way to calculate this Brownian diffusivity, Bi. It's similar to what we discussed before. So for this Brownian diffusion coefficient, okay, or diffusivity Bi, will be just equal to the kT. Remember, the small k here is the Boltzmann's constant times the temperature, and then you have this divided by 3 pi times the mu. Mu here is the same as the gas viscosity. I use a different symbol. Maybe just use the same thing here. And then also related to the particle size that you are interested. Okay, so this is the dp is the particle diameter, right, of the particle here. So also in this case, some terms are cancelled here. Is because we just assume your Cunningham coefficient is just equal to 1. So I just simplify some of this expression here. So now you can also using this term, right? So you can see this to calculate your co-occlusion coefficient, like K12. So that would be equal to 2 pi times this particle diameter of your particle 1 and the particle diameter of your type 2 particle. And then you can calculate, right, this D12. Now you know the D12 can be calculated or expressed in terms of D1 plus D2, right? D1 is the diffusion coefficient, right? The Brownian diffusion or the Brownian diffusivity of your particle 1 plus the Brownian diffusion or the Brownian diffusivity of your particle 2. So you can calculate this, right? So you can substitute this into here, right? Into these two terms. So by doing this, So by just substitute these, or you can just calculate this, you can substitute into the inside. So you can also calculate the cooperation coefficient. Okay, K12 be equal to this small k. So now you can calculate the cooperation coefficient, okay? Say when you have this kind of a cooperation between two particles with different size, say this is the dp1. So now we use the diameter, we don't use the radius. So this is and you can see this is the expression. This is just a 2 times the k. Again, k is the Boltzmann's constant times the temperature divided by some constant. Here is the 3 times this viscosity of your air. But the most important thing is you can see from here is the cooperation coefficient, okay, is a kind of related to the size, right, of your two particles, okay. It's kind of an expression, okay. Say for your particle 1 and particle 2. So that means that you can intuitively think about this cooperation coefficient. The kind of the changes, right? So if you have different particle size, or if the ratio, say the ratio between your N1 and N2, so this will affect your cooperation, right? Coefficient. So let's say, so I try to draw you the result, okay? And then we want to have some discussion here. So let me just draw the figures, and now we try to explain to you. I think this is a very important idea or message. So somehow, so we should get from here. Okay. So first, let me stop here and then explain to some of the terms. So because we are looking at the cooperation, right, between two particles with different size. So the x-axis here, so is the size of, say, your N1. So you can say this is 10 to the power minus 3, 10 to the power minus 2, 10 to the power minus 1. This is 1 and 10 micron in diameter. Okay. And then the y-axis here is the cooperation coefficient. So you can calculate this. But of course, you need to define your particle size of your N2, right? So because of the N2 can also have different size. Okay. So again, so the x-axis here, so I just try to repeat. So the x-axis here is the size of your N1, say from 10 to the power minus 3 to all the way to 10 micron. Okay, this is the size of your N1 particle. So this is the cooperation coefficient, say from 10 to the power minus 10, all the way to 10 to the power minus 4. So the unit usually we use the volume per second. And then the number, the line I show you here, is the size of your N2. Okay, so at least this, and let me, I'm not sure you can see. So let me so I just this kind of dotted line. So this dotted line, so you see there's a hump here, right? So there's a hump here. So this is assume your two particles have the same size. Okay, so that means you can see this is a dp1 equal to dp2. So that means they always have the same size. Okay, so they will have the same size. That means this is a special case that N1 and N2 have the same size. So this is, and then if you look at the y value, then that will be their correlation coefficient. Okay, and then you can also have your dn2, right? So your N2 have different size with your N1. So this is the size of your N2. Say this is 0.01 micron. So this is 0.1 micron. So this is 1 micron, and then this is 10 micron. So all this is your dp2, size of your N2. Are you okay with this? Okay, right? Okay. So now, I think there's some important message. So we want to look at from here. So one thing is you can observe is, so let's say if you look at just the size here. So when you have very small dp1, but if you say the ratio, or if you say you have a larger dp2, okay, so because you can see, just look at this, so you can compare this value, say this value, this value, this value, right? So that means that if you have a very small dp1, so just in this case, if I draw a table for you, okay, so maybe I would say this is a dp1 with a different size. I'm not sure how to present, but you can see if I fix my dp1, it's a 10 to the power minus, say, maybe just if I set my dp1 equal to 10 to the power minus 3 micron, okay. So if I change my dp2, okay, so now this is my dp2 size, and then this is the K12. So you can see, so if say my dp2 have the same size, say 10 to the power minus 3, so the value here, maybe you can say 10 to the power minus 9. If my dp2 now is become 0.01, right, 0.1, so maybe you can say 0.001. So if just a 0.01, right? So the value can be maybe around something of 10 to the power minus 8. So don't worry about the exact value. But if you go to a larger value, say 0.1, 10 to the power minus 6, and then you can have a 10, have a 1, 10 to the power, maybe you can say minus 5, and then you have a 10 to the minus 4. Okay. So, but one thing you can see from here, or if you look at the trend, sorry for the, but don't worry about this. If you look at the trend, is if I fix my size and then I increase the size of the other particle, say now this is your BP2. So what happened to your correlation coefficient value? So that would be increased, right? So you can see, so if they have the same size, very small size, but if you say if you have a small particle but has a large dp2, okay, if you have this kind of combination, your correlation coefficient will increase, right? Will increase. Does it make sense? And also you can see this is depends on the ratio, right? So more precisely, I mean, you are looking at the ratio, say of your dp1 and dp2, but I just write down the ratio here for dp2 over dp1. if this ratio, right, if this ratio increase, so you can also find that your cooperation coefficient increase. Okay, does it make sense? So based on the value, okay. So then you may ask us why this happened. So, but before we explain to this, I also want to give you some observation from this graph. So first, so you can see, so if you look at, let's say you just focus on, you get the same size here. So basically you can see you have a hump here, right? And then you have the smaller value at both ends. So what's the implication? So one thing is, I just want to first highlight, if you have a small particle, so versus small particle, so you have a two small particle, okay. So you can find that if you have the two small particle, so their cooperation coefficient, right, is small. And also you can see on the other hand, so you have a two particle is a big. You have a two large particle, their K value is also small. And then it is somehow in between, okay? In between, right? So you have a larger value. And also another observation, right? You see that if the ratio, right, between these two particles increase, okay? So you have a larger size difference, say, that means you can argue, say, some small versus big, then your K value is large, okay? So this is about the observation. So now we want to see why this happened and how we can explain this, okay? So one thing we can argue is that if you look at the coagulation happen, so there's two important things. So one is we call the cross set of the surface area, right? Surface area, say for the collision. Okay, so of course, if you want to have this coagulation or collision can happen, right? So you want to have a large surface area or targeted area for the collision to happen. Okay, this is the one thing. And also, if you want to consider, if you want to have a collision happen, right? You also want to look at is the mobility, right? The particle mobility. Because you need to have the particle moving around, so they can hit each other, right? So this kind of a collision. So therefore, you want to look at the mobility. So this is related to their Brownian diffusion coefficient, right? Or you can say the speed, right? That kind of the speed here. So now if you know this as a two, say kind of a crucial parameter to determine, right? Say the coagulation. So now we can come back to these 2 points. So why we have this kind of observation? First, so when you have the two very small particles, so why the coagulation is small? So of course, for two small particles, so of course you know they will have a higher mobility, right? Particle mobility. So there's a larger Brownian diffusivity, right? Or higher thermal speed. But the thing is, because of their small particle, right? Their targeted area, okay, or they have a very small cross-sectional area, right, for collision. So that means that even they can move around very quickly, they have a high speed, but their surface area for collision is small, right? So therefore, overall, so their the coagulation, right, or the collision will become small. So even you have the speed or mobility, but you don't have your target surface area is small. Does it make sense? So then you can also make the same argument here for large particles. So now you can see, so there's the opposite, right? For large particle, so you have a large surface area for collision. But the problem is for large particle, so you have a slower speed, right? The slower speed. Okay. the slower speed. So therefore, so even you have a large surface area for collision, but you have a lower mobility, a lower speed. So therefore, overall your value is smaller. So therefore, it's somehow in between, right? So you will have a higher K value. And most important thing is you can see, right? Also you can see from this table I just show you, right? So you can find that. So this value, right? This cooperation coefficient increase rapidly, right? Like I mentioned, when the ratio, okay, the ratio of the particle of the diameter. So let's say the ratio of the particle diameter, say between increase, right? So you can see you start from, if you have a very small particle with a small particle, just 10 to the power minus. If you go to a large particle, say 10, with a small particle, just a 10 to the power minus not 3 micron. So this is 10 micron. So you can see your value become 10 to the power minus 4. So about 5 order of magnitude, right? So you can see here. So therefore, you can see this is related to the ratio. So again, so overall, this is due to kind of the synergy, right, between the two particles. Okay, does it make sense? So because of, again, so the large particle, you can argue is in this case you can have some large particles around. So, but they have a kind of we call the sluggish, right? So they just they don't moving around quickly. Okay. But the thing is that if you have a lot of small particles around, okay, so they can provide large surface area, right? Say for high speed, small particle. So even they just present that they don't move around, but you remember, so you in your system now you will have a number of small particles, right? So quickly moving around. So that will eventually enhance the kind of the collision or coagulation. So therefore, does it make sense? So therefore, you can see that for the coagulation, I hope that you have the idea that you have two very small particles. Okay, so you can see that the coagulation coefficient is very small. Okay, and also you have two large particles. So basically, they just stay there. They don't move around, right, for collision. So they also have a very small value. But in between, if you have the ratio, right, if you have some large particle in your system and also some small particle, right? So in that case, so you can have a larger kind of a cooperation coefficient. So this is because even you have some large particle there, right? So they don't move around, but they provide the surface area, right, for the collision with the high speed small particles. Does it make sense? So therefore, you can see here, right? So let's say you have some small particle, but if you have some large particle, then you can see the cooperation coefficient increase significantly. So therefore, you kind of this kind of observation. So any questions so far? Any questions so far from the class? Okay, so these are just to give you kind of a qualitative analysis. So basically, you can also by looking at, or if you examine this equation carefully, you will also get the same conclusion. Okay, but here you just take this out and then qualitatively discuss it here. Okay. And also one thing is we have discussed. So we have discussed the size change, right? So I still want to have some discussion about the size change. I still want to have some discussion for the size change. Because you can see here, right? So the last time we talked about is you have two particles with the same size, right? So now you can see if we assume the mass is constant, right? And then if you assume all the collision can give you the same size, so you can see if you want to double the size, that means double the diameter of your particle. So you need to decrease the number concentration, right? By saying maybe a factor of 9, right, or significantly. So, but I also want to see, but now you can see here, right? If you really want to favor the coagulation, so what will happen is that most of the time, so you will have if you have a high coagulation, is when you have a small particle, right, together with some large particle. Okay. So I want to see how it will happen. Okay, so let's say you have a collision between a small particle and also a large particle. Because of this, you can see here, right? So in this case, this is let's say the coagulation is favorable, right, for say a large and a small particle, right? So of course we know, so you can some collision happen, and then you can have some new particle form. And then in this case, I want to study, say, the small particle and then collide with a big particle, okay. And then we want to see, so how the size change. So let's say if I have a particle, small particle is at 0.1 micron. And then for the big particle, so let's say it's a 1 micron. So I want to see, so how the size change, okay. So of course, the calculation is straightforward. So you can just say after collision, right? So you just add the mass together. So just assume you have a M1 and M2. So that means a large particle and small particle here. And then if you assume they have different size. So let's say this is a 0.1, okay. And then the other one is just a 1 micron. Right. So this is the one. And then I just want to know the size after the collision. So if you know the mass, and then you can back calculate, right? Assume a size or diameter for your new particle. So you will find that your new particle size will be just 0.00033. Right. So this is your new particle. So because based on the mass, right? So for a new particle, so you can use this mass to calculate the diameter for your new particle. Let's just skip the step, I think, so you know how to do the calculation. But the one thing is that you can see here is if you have a collision, say small and big. So here I define is a 0.1 and 1 micron. So now you can see here is basically the size does not change that much, right? So you can see the diameter of the larger particle, right, does not change significantly, right? This is and also you can see the size of the new particle, right? So this is the size of the new particle. So basically, it's just about the same as the large particle. Do you see the point? So basically, because this is just a large particle, right? So one thing you can see that the diameter, right? The overall idea is that the diameter of the new particle is just about the same as the large particle, right? If you just have one collision happen. So that's why if you really want to change the say the size of the particle, so you need to have a multiple collision, right? So if in case you have a small particle around here. Okay, is there any questions so far? Okay, so again, what we derive here, the equation we just show you here is again is for the continuum between So again, so if you really want to move to say transition or free molecular regime, free molecular means that sometimes we call kinetic regime. So of course, you also need to do the correction, right? So most of the time, so one way to do the correction, say with a different size. So again, they just times the beta, but just times the beta, okay? So again, so it depends on, we don't go into details, but the only thing is it depends on what condition we are talking about. So again, remember, so most of the time when we derive this equation, we are in this kind of, we call the continuum regime, okay? Assume a perfect absorber. The only thing I want to highlight is, so when you go to the free molecular regime or the kinetic regime, okay, because most of the time, okay, so when we talk about the collision, right, so you just stick together, right, so you just assume, okay, you can argue, right, the sticking coefficient, okay, the probability, okay, you just equal to 1, right, so you can argue this is a probability 100%. So they will just stick together. But I just want to let you know is if you go down to the free molecular regime or transition regime, so this is not always the case when the size becomes smaller and smaller. Okay. So every time the collision, you are not talking about some of we call the perfect absorber. So this may not be a good assumption for small particles. Okay. So when you go to the transition regime or the free molecular regime. So therefore, always the idea is that this beta is always a decrease, okay, get smaller than 1. Okay. So I just want to have this discussion. But of course, a different study will give you different expression for your beta here. So any questions so far? But remember, the beta is always smaller or equal to 1 because you compare to a value, right? So in the continuum regime. So any question from the class? So are you happy with the explanation here? Why collision between two very small particles is small for the cooperation coefficient. So for also we have a small value for the collision for two large particles. Okay, so that's somehow in between. So you have the larger value. So that's why it depends on the ratio. Okay. The diameter of the particle that you are interested in. And then we provide the explanation for you. Because this is related to two important parameters. One is kind of the speed, right? The Brownian motion. And the other thing is the area, okay? Or the targeted area for the collision. Okay, so we also want to do some mathematical discussion to look at. So when you have this kind of a co-oculation, okay, so how you will change your aerosol number concentration. Okay. So let's say you have some aerosol population, okay. So we want to look at the evolution. Say if you have a particle, right? With different size, that means we are talking about the evolution of a polydispersed. So polydispersed means that you don't have a particle with a single size, so you have a particle with a size with different size, right? You have a distribution, right? And then if you allow this a coagulation or coagulating, and then you're looking at the aerosol population. Okay. So to understand this kind of coagulation, so we can also draw a picture like this. Okay. So you can argue, right? So when you have this kind of a coagulation, just like you have a different monomer, or you have different size of a particle, right? And then you can just hit together and then you add together. For example, one typical example is that if you have two, say, just a monomer, and then you combine and then you form a dimer, right? or you can have a dimer combined with a monomer, give you a trimer, right? So you can present in this way. So basically, you can also argue, say, if I want to form a Kmer, so that means that you have a, say, Kmer means that so I equal to 1, that means that you have only one particle, K equal to 2, so, or I equal to 2, so you have a dimer of just a 2 particle sticking together. And then you can also have K, you can have N number of particles, right, sticking together. Or sometimes you just say at a Kmer, right, at a given time. Say Kmer at a given time. So you can also look at the number concentration of this kind of, we call the Kmer, right? So we can have 1, 2, 3, 4, 5, 6, 7 here. So to form a Kmer, so we can also argue is just have K minus J combined with a Jmer, right? This is K minus J, and then combine with another J, so you add them together, will give you the Kmer here. Okay. So we try to kind of first look at, so let's say review some of what we call the descriptive, okay, representation. Okay, so just to look at, so we don't look at the continuum equation first, we look at some of the descriptive representation. Say of the distribution. So basically, you can also think about is when you have this kind of coagulation, right, between two particles, okay, with different size, you can have 1, 2, 3, 4, 5, and then you try to form a size, say the Kmer, okay, so we can argue with this, okay. So we try to find a mathematical representation for this kind of a coagulation. So basically just adding different size of your particle, right? And then you first form a size that we're interested in this case, Kmer. Okay. So now if you want to look at the formation of this kind of Kmer, or if you want to look at their concentration, right, at a different time, okay. So now if you look at the Kmer here, so say a different size that we are interested, okay. So remember, so you can have a kind of a formation, right? So basically you can find a right combination, right? And then that will give you size that you are interested. So this is kind of the formation, right? This combination. But remember, once you form the K, so the K will also collide with other molecule, right? And then can grow, right? So they can also grow. And in this case, we can say this is a K because once you form the K can also collide with all other particles, right? And then they can grow further. Then we can say this is called the decay, right? So therefore, if you want to look at so how the concentration of your Kmer, right, as a function of time. So you want to look at the two processes. One is the formation, right? That means that just have the right combination give you the Kmer. But once you have this kind of the Kmer, right? So they can also have this collision with all other particles, right? And they can grow. Maybe become K plus J or something like that. So then you have a decay, right? So you need to consider these two processes here. So first, we want to look at the formation rate. So let's say we try to write down the formation rate. So this is the J. So let's say Fk. JFK. F means the formation of this Kmer. Okay, this kind of the Kmer here. So to form the Kmer, so if you look at the equation. Okay, if I want to look at the formation rates of the K that I'm interested, of course, don't worry about the summation. So first, you want to look at the cooperation coefficient, right, between this Kij and J, right? So that means, right, so this is the cooperation coefficient, right, between the Kij, K minus J, and then with the J, right? So come on, this is the cooperation coefficient, right, for these two particles, right? One is the K minus J, and then this is the J, right? So that because when they stick together, right, that they combine, so they will give you the K, right? And then you're looking at their concentration, right? This is the concentration of your K minus J, and then this is just the concentration of your J here, okay? So of course, you can have different values, so you just do the summation, okay, to do this. This may be complicated, but we can give you some examples. So let's say we want to say form a K must say is 3, okay? So let's say I want to form a K-mer. Now the K-mer is a trimer, right? Trimer means the 3. So if set the K equal to 3, right? K equal to 3. So then you can just write down this equation, right? So that means I want to say form a formation of a trimer in this case, right? So this is a formation rate of my trimer, right? Set K equal to 3. So now if you look at this, so you look at this, I think you know how to write down the equation first, right? So you have this cooperation coefficient is a 2, 1, and then times the N. So I think that you know this is the summation, right? So from J1 to K minus 1. Okay, and then you can say J equal to 1. Okay, this is now case, this is 2. And then you can, if you do the substitution, right, to this, so you have these two terms. So I think this is to make sense, right? So how you form the trimer, you are looking at this is a dimer combined with a monomer, right? And then you're looking at the coefficient, right? So this is a cooperation coefficient, right, for this N2 and N1, right? And also you can, the other way is that you can also, if you by mathematical expression, so this is also the cooperation coefficient, right? Between 1 and 2. So also 1 and 2 particle, this is also N1 and N2. So this is from the mathematical expression here. Does it make sense? So this is how you can form a trimer, right? Okay. And then if you, because you can see here is because the cooperation coefficient, say 2, 1 will be equal to 1, 2, right? Because they are the same. So we are talking about the cooperation coefficient, right? Say N2 relative to 1 will be equal to 1 relative to 2, right? So they will be the same. So then if you're using this equation, now you can see the formation rate of your trimer, right? Will be just because of this term will be equal to this term, right? Because of this cooperation coefficient will be equal to this one, right? So we just 2 times the K cooperation coefficient, say 1, 2, and then times the concentration for N1 and N2, right? So this would be the case here. Okay. But now if you think about this, is we can see if you times a 2 here using this expression. So kind of like you double count the calculation, right? Because of this, it just happened one time, right? We just have a 2, right? Or say a dimer collide with a monomer and then give you a trimer, right? So you just do one happen, right? But in this case, if you use this expression, right? So you will count twice, right? The collision will count twice. So therefore, people will just multiply 1/3, so 1/2 to cancel this effect. Okay. Because if you do this summation, so you will double count, okay, the collision. Because the collision will count twice. But like I mentioned, right, if you want to form just a trimer, right, so you just have the collision between the dimer and a monomer, okay. So, but in this case, if you're doing this, so the kind of the collision. So we'll count tracks, okay, if you use this expression. So therefore, so you want to multiply one half, right? To avoid this, we call the double count. Okay. And also, like I mentioned, right? So once you have this K form, so say if you have a trimer form, so what will happen in the system? So you still have some monomer and dimer, right, in the system. They can also collide with your trimer, right? And then that will give you the decay, right? Because they can grow, become larger, right? So therefore, you can also have this we call the JDK. D means the decay. So like I mentioned here. So this is just a consider, so you can have a Kmer. Once you have a Kmer form, okay, so you can always have other molecule, right, collide with your Kmer, right? So therefore, Kmer, you take this out, and then you have this kind of a cooperation with all sides, right? Because you can just have a monomer, dimer, trimer, and also all other sides. So therefore, you consider all the ways to infinity here. Okay. So the idea for this equation. So of course, you can put this here, but this is a constant value. But the idea is that you can have a depletion, right, of a Kmer. And also there's another term we call the agglomeration. That means that you can say cooperation or collision with all other. So that's why you need to take all particle, right, with different size. Okay, so therefore this is to become an infinity here. Because if you take our cases, so once you form this trimer, right? So you can still have the monomer and the dimer around, so you can collide with this trimer, right? And then you can just they can just grow further. So therefore, to determine, right, the concentration of a certain size of the particle, in this case, a Kmer here. So you have these two processes, okay? And then if you combine these, and then if you want to look at so how the concentration of your Kmer, okay, change with time. So then you will have this expression. So one is the formation, right? So remember, this is the cooperation coefficient, right? To form a Kmer. So you need to know the cooperation coefficient, right? It's a K minus trace react with a collide with a Jmer, right? To give you the Kmer, okay? And then you need to know the concentration, right? For these two particles, okay? And then this is the formation, because if you do the summation, so you have a double content. So we just have to multiply one of the two here. So like we say here. And then minus, remember, so once you form this KMA, so they can also collide with some other molecule or other molecule, right? So therefore, you have this KMA times this cooperation coefficient, KMA with all other molecule, right? So therefore, it's a Kj here, and then times all other molecule, Nj, and then you do the summation. So then this equation, so will give you, we call the descriptive cooperation equation. Okay, so do you have any questions so far from the class? Okay, of course, in the lecture notes or in the textbook, so we can also write down a continuum or continuous. So I don't show it here because of the time, but we can also write down the continuous cooperation equation. So basically, just change the kind of the notation we use here. But more important thing is that now you have some ideas about this term, right? So all this term, if you know the ideas from this, we call the discrete cooperation equation, okay? So this term here, so I think you have no problem to write down or understand the continuous cooperation equation, right? So I hope that now you will see, so why you have this, so what's the symbol here means, and then what's the equation here, and then why you need to do the summation, right? Okay, because we can also extend this to say 4, 5, 6, right? Then we can extend to all the way to the KMA here. And then remember, so you have this formation rate, you will also have this kind of the growth. In this case, we can say it's a decay rate, so you need to have, because you can collide with some more other particles, right? So you have this term. So why this has become K, right? Cooperation coefficient is the Kj here, and then you times the Nj. So if you understand these, so I think there's no problem for the continuous equation. So do you have any questions so far for, say, formation of a KMA here? And also just put down some number for illustration purpose. So any questions? Okay, so maybe we don't take the second break, so I think just a few more things. Okay, maybe about, yeah, so maybe let's take a 7-minute break here. So let's come back at 1:50. Okay, so let's take a short break here. So after that, so you have this equation, right? So now you have some idea about the cooperation, okay? And then you have this cooperation and then formation of a KMA, right? Okay, so now we want to have some analysis, okay? So how the cooperation will affect, or how affect the evolution of a, say, aerosol population, okay? In case initially you have some polydispersed particle, and then you allow the cooperation occur, so how you will affect, okay, your particles distribution. Okay, so we're going to talk about this after the break. So let's take a short break here. So so we can come back at 1:50. Okay, so let's take a 6-minute break, and then we try to finish a few more pages here. Okay, finish the last section for today's. So of course, this equation, right, we call the discrete cooperation equation, right? So tells you, say, the formation of a KMA, right, due to the cooperation, right? So you have two processes here, okay? So of course, you can basically just solve this equation, but I want to just say if we can solve this more like analytically, okay? To solve this equation, I just want to say one thing is, so in case, so let's say if we can assume this cooperation coefficient is constant. Okay, so let's say this is K is equal to constant. So I understand, so this is not the case, right? We show you that, so this K value, right, the cooperation coefficient, right? So of course, it will depends on the size, right, of the two particles, right? So it will change. And in fact, can change it significantly, right? It depends on the ratio of the two particles. But so let's say for some classroom discussion, so I want to have some discussion here. And then let's say if we assume, say the K is a constant, okay? So I know, so this maybe have some limited application, but I just want to see, want to provide you some insights, okay? So about, so how, say the population can affect the evolution of our aerosol population. So let's say if you stay with me and then assume, say, these cooperation coefficient, okay, does not depend on the size between the two particles, and it's always equal to say a K value. So that means these are just some constant, right? So these are the constant. So now you know that, so if this is a constant, so you can take this out. So you can just take this a constant, right? So you can just take this out. So now just nothing. So basically, I just try to repeat this equation, but I assume this K now. We just assume it's a constant, right? That's not depends on the size of the two particles. So therefore, the K is turning this out. So therefore, if you want to look at so this equation, just say I just put the T here, means so that remind us the concentration of your K will change with time, right? So it's a function of time, and also all this concentration, right? Say the J or the K minus J and also the K J here is also a function of time here. Okay. So now we just want to do some analysis. So if you look at this term here first, so this is a summation, right, of all your particle size, right? Say from 1 to so from 1 to infinity. That means this will include all the particle size, right, at a given time. So therefore, if you look at these terms, right, if you do the summation, right, so basically you add the number of particles of different size, right, all together, right, all particle size. So therefore, this term, right, so if you do this assumption, right, so this is just your total, right, your total number of particles at a given time here, right, total number of your particle, right. Because you just add all the number of your particle size, right? So this is NT. NT means this is the total number of particles at a different time t, right? So this is the time t here. Okay. So now, because one thing is that we want to look at is say the whole population, right? The evolution of the whole population. So now you just are looking at say a different KMA, right? So different size. So how they change with the time. So of course, you can also look at so how the total number. Want to look at so how the total number is concentration. Remember, we want to look at so how the total number concentration say change with time. Okay. So we can do this is we just add them all up, right? So this is just a KMA, right? So if you want to look at so how the total number concentration with time, so we can just we can also do the summation, right? Or say summing, right? So we just add all the say the KMA say from 1 to infinity, right? So we just add them all up, right? So then I want to know so how the total number concentration will change, because of this you just give you say the number concentration change with time with the KMA, right? If I want to say I want to look at the total number concentration will change. So basically I just consider all the particle size, I say from 1 to say infinity. Okay. So then I can just do the summation here, right? So if I do the summation, so now this term I will change to become, so how the total number concentration, right? NT change with time will be equal to, so now I do the summation, okay? K equal to 1 to k equal to infinity, just rewrite this. So basically what I try to do, you can see I just add another summation, right? Say from K1 to infinity, right? So then I will give you, say, the total number concentration change with time. Okay. So because in this case, so now we are setting, say, case is from 1 to infinity, right? So if you look at this term here, is now remember the case is now is infinity. So if you're doing this, so if you look at this summation here, so you will find that this is what we call the double summation. And then every time if you say summation, say from 1 to say J1 to K infinity, right? So you will find that, so this will give you N2. Okay, so just give you the N2 squared. Okay. And also, if you look at this term also, if you say the k equal to 1 to infinity, and then you do the summation of all the k here, right? So this will also give you the NT, right? The total number concentration. So therefore, this is also give you the N2 squared, right? T. So you also have this, if you combine these two, so you also have this N2 squared. So if you just do this, all this summation, so you will find that if you make this assumption, say all the cooperation coefficients, so it's constant, okay, and then I consider the summation, say from K1 to infinity. So basically, I consider all the particle, right, with all the size, right. So you will find that. So you get a very similar result. We get is equal to 1/2 k times the N2 squared. Remember, this is also your total number concentration at a given time t. Okay. And then if you know the initial condition, right? So if the N say initial condition, so just the N0, right? So if you set this is your initial condition, so that means at time equal to 0, so you have your initial number concentration, say N0. So if you solve this, so you will find this equation. Okay. So if you're solving this equation, I assume you have no problem solving this. You can just solving this, the total number concentration change with time will be equal to 1/2 times the k. K is the cooperation coefficient constant for all particle size, right? Range. And then it's just the N2 squared, right? So with N2 squared. So if solving this, so you will find that so your concentration change with time. Okay, the total number concentration change with time, or at a given time, will be equal to N0 divided by 1 plus t is the time, divided by this tau c. So tau c is we call the c is the coagulation. So therefore the tau c here, so we also give you the definition here, right? So tau c is 2/k. K is the coagulation coefficient. right? We set here, and then times the n naught. So this tau c, we call this is a characteristic time scale for coagulation. So basically, if you look at the definition, you can just consider, say, the time, okay, required to reduce to, say, 50%, right? You can see n2 divided by 2, so 50% of your initial number concentration. Okay, so this is the tau c. So if you can calculate the tau c here, right? So this is the coagulation coefficient. And then if you know your initial number concentration, right? So we can calculate the tau c. So again, so remember this tau c means the time, right? So you require to say reduce to 50% of your initial number concentration. And then you can put this, so this will show you how your number concentration change with time. Okay. So we have this expression. Okay. I just want to show you some number, is some typical number. Okay. So let's say in the ambient air, so usually the aerosol number concentration, say is 10 to the power minus 4, so 10 to the power 4 cm cube number of particles per cm cube. And then the coagulation coefficient, so let's say we set a small value, say 10 to the power minus 10. So avoid the overestimation. So you find that this is more like the typical, okay, atmospheric condition. We just try to do some lower limit here. So you will find that to kind of, if you put in this number, so you will find that the tau, or you just calculate the tau c. So let's say you calculate this tau c, it's about 55 hours, okay. So in case you just allow you have some particle in your system, okay, with this number concentration, and then you have this kind of overall average, okay, coagulation coefficient is 10 to the power minus 10, so you know it's a lower limit, right? So the time is about 55 hours, okay, about 3 days or 2 days. So then you will reduce the number concentration to about 50% of the initial number, okay, for the ambient. But I just want to show you that because like I mentioned to you, right? If you look at the chamber study, okay, for those that you have a chance to study the environmental chamber studies, okay, so in that case, so you will find that the number concentration is higher, usually 10 to the power minus 6, sorry, 10 to the power 6, okay, particle per cm cube. And also, if you still use this 10 to the power minus 10 to calculate, so you will find that for the environmental chamber, so the characteristic time scale is about 30 minutes. So therefore, you can see that the coagulation can be an important process, okay, that could happen in some environmental chamber studies. So therefore, this will significantly affect your aerosol particle size. Aerosol number concentration, of course, eventually may affect your particle size. So this is some process, so especially for those if you simulate, okay, if you simulate the aerosol evolution, say the number concentration or the size distribution, so you really need to consider these, because 30 minutes, so you just decrease 50% of your initial particle number concentration, okay. So this is a very important process, okay. So therefore, this is also limited. So how long you can run your chamber study, right? Because 30 minutes, so you lose, okay, or your number concentration reduced to 50%, right? And then that means another 30 minutes, so you reduce another 50%. So you need to be worried about this, okay? So of course, it will slow down a little bit, but you know this is can have a significant impact on your measurement. Okay, so one last thing I want to show you is more, if you have some ideas about this analysis. So I just want to show you, so how you're going to evolve. Okay, so number concentration evolve. Okay. of course, you can always plot this equation in your model. You put down some numbers, so you can always easily calculate this. Just I want to show you in a graph for the conclusion. So in case, so this is your size. So this is your size of the particle. So let's say this is your concentration. So let's say initially, so you have a distribution like this. Say time equal to 0. So this is your initial concentration. And then, of course, when you allow the cooperation to happen, so how you will affect this graph, okay? So of course, you will see that your area will decrease, right? Your area will decrease over time. So when your time increases T1, T2, and T3. So the reason you will see this decrease is because your number concentration will decrease, right? You see my point, because this is due to the effect of the cooperation, right? On your number concentration. But because we plot this is the number concentration, okay? So you will see this as a significant effect. And also because remember, so even you have this number significant decrease, but of course we don't draw clearly, but of course your size will increase, but like I mentioned, so the size will not significantly increase, right? So will not significantly increase. So of course it depends on distribution, but we show you that, so if you want to say somehow double your size or increase your size, so you need a number of calculation, right? So therefore your size will shift a little bit, but you see more decrease more significantly. The number concentration decrease more significantly, but you will not see a significant shift to the right, right? So you will not say on something like this, right? So you know this is not happening, right? Especially also in part of the log scale, right? So usually you will not see much changes in the size, but you will see a significant decrease in your number concentration. Of course, your volume will change. Okay, so your volume will change because if you start the other way, this is your volume, and then this is to say your number volume concentration over time. Okay, or maybe say initially we don't have any large particle, so this is time equal to 0. So of course, so this is the volume concentration. So this is the particle volume. So of course, when you go through the time, so you will see that your number concentration will decrease. So you will eventually form some larger particle, but without it, but that's significant, right? So this is you need to be careful here. So this is just another way to plot. If you look at the volume, of course, you will see the increase in the particle volume, right? So because you will form some larger particle here. Okay. So any questions so far? Okay, I think this is very much I want to be covered for the coagulation process for today's classes. So, but before we leave, so do you have any questions from the class? Okay, if not, then I think so. I also look forward to your presentation and also your literature review or your term project, right? So in case you're a PhD student, you need to also submit your literature review. So I also look forward to your report and also your presentation. And also that would be formally that would be the last lecture, okay, for this course. I hope that you have some ideas about the aerosol science and chemistry and physics, and also appreciate why the beauty of some of the aerosol science. And hopefully you get something from the course. Okay, so again, so if you still have any question about the course materials and also the assignments, so feel free to contact me and also the TA. Okay, and then hopefully, so you enjoy this course, and then I will hope to see you soon, okay, in person on campus. Okay, so thank you so much. Okay, bye-bye. So that would be the end for today's lecture. Thank you, bye-bye.